And I set the volume here, and you can see it's already starting to saturate. But when I look at this part here, it's the same way. You know, at 21%, it's already starting to saturate. And that's one way to test it, right? You know, is to basically watch it now, you know, and see how it comes out through the speakers. Okay, so let's give it a try. And let's use the one from today to try it out. Okay, where's the volume control of this thing? You're right. I cannot hear anything. So let's see. Oh, that's 8%. 78%. It's still not. Well, maybe the volume control is not set right correctly. Built-in audio setting. Okay, the recorder is indicating it's recording. It's you know, it has the full range, but yet, you know, when it's playing, it's not the playback doesn't have anything that I can hear, not through this speaker. What am I gonna do? Yeah. Yeah.
And then, but when you turned it down, it was really quiet. I turned up my speakers, and you could hear it, and it basically sounded the same. Like it was still maxing the mic.
Okay.
Like the mic.
Well, this is my solution. Take matters into my own hand when the alternative, when all alternatives fail, you know, then I just have to do it the same way as we usually do it, right? Oh, this is funny. It's actually doing the cyclic thing. It has gone through a whole cycle already, so it's watching the player play the recorded one, you know, and it's starting to loop already, as you might have noticed. Yeah, if it keeps going for a while, it will keep going like this. It's kind of like a mirror, like two parallel mirrors, so you can basically have infinite reflection, except this is not reflection. This is actually not left, right, reversed. Alrighty, fine. We'll use the usual way of doing things. That is proven to work. Huh? Yeah. Yeah. Huh, that's odd. Okay, well that's okay. We can always just, you know, change it back to the usual way. That's using the external mic now. It should start to work.
I like the other one better though.
Yeah, unlike the other one, but I can try it too. Okay, so we'll go ahead and watch our own video again. And fast forward all the way to the end where, nope, it's still not showing anything.
The output device?
The output device may not be correct. The playback is using a built-in audio. HDMI? No, nothing. Nope. Well, I just can't hear anything from the output. Alrighty. But because the recorder is actually recording, if you look at the volume control thing, it's actually having the usual way. This is going back to my external mic. It's not or the standalone mic here. So it should be working now because, you know, that has been working for a long time. So unless I do something to mess up the actual recording script, which I didn't do a single thing to the script, so I think it should be okay. So I'm gonna take this off because I'm not gonna use it today. Alrighty. So how was the homework assignment? It was okay? Alright. Did it help you understand some of the concepts like comparison, stuff like that, how memory is organized, addressing modes, stuff like that? Okay, so I have a new homework assignment for you, and It's really kind of the best way to study in a way because it makes you not only to read about the material, but it also makes you think about how to apply what you have learned in this class. So, in fact, I would say, for a class like this, the time when you learn the most is not when you read, it's not even when you're here, it's when you debug your program. Okay, I would say that is when you start to realize, oh, okay, so this is how it works, this is how that works, and so on. Okay. All right. Let me show you your new homework assignment. It's actually easier than the one that we have before. Okay, I didn't sign in correctly. Let's try it again. There we go. All right. So the new homework assignment is actually easier, and you can tell me whether it really is easier or not, because I really think it is. Oh, no, it's one chapter before that. There we go. Okay, it's called string reverse. Okay, it's a little bit, oh, it's not, you cannot see it yet because it's still hidden. I have to unhide it first. So let me go ahead and unhide it. Settings, show, save and display. There we go. Okay, so this is your new homework assignment. It's called string reverse, and don't even bother to look it up. There's no such C function as string reverse. But as the name implies, I think most of you know what it's supposed to do. Okay, it reverses, a null terminated string. Okay, the destination is not the same as the source. Okay, so there is a designated destination. You keep the original string just the way it is, and then you have another storage area for the reversed string. So I give you like a starting point. The starting point is like this, and this is something that we haven't seen before, but I want to do it this way because one, it is actually in the notes. Okay, so if you have read the notes, it's actually in it. The dot, okay, the single period is basically the current point of this particular section of memory. Okay, so it's saying, well, let's see. Actually, I don't want it to be like this. Okay, this is wrong. I have to fix it. Now that I'm reading it, try to explain it's like, whoa, that's wrong. Okay, so I'll go ahead and change it first. Fix it a little bit. And when I'm fixing it, you cannot really read it because the way it's entered is, part of it is entered in HTML and part of it is entered in a different way. Okay, so we have original being a colon here, dot equals dot plus 256, and then reversed is just another label, and then we have dot equals to dot plus 256. That's the way it is. Okay, there we go. Save and display. Back to the normal view. There we go. Okay, so original is really defined the same way as any other label that we have defined in this class. Okay, so that's nothing mysterious about original as a label. The next line is kind of like a dot fill 256, but it's not. A dot fill 256 has an implication. It implies those 256 bytes are initialized to what value? To all zeros. Okay. So that means, some people will look at this and go like, well, since we already have the null terminator filled up the entire space, we don't have to specify the null terminator, both in the original string and also in the destination, which is the reverse string. By doing it like this, I'm basically telling the assembler and say, advance the current address by 256 bytes. Did I tell the assembler what to fill it up with those 256 bytes? No. So that means you can no longer make that assumption that these 256 bytes will be zeros to begin with. Okay, so do not make the assumption that everything is null filled to begin with. Okay, so that's basically what this line is. Reversed is another label definition. We know this is a label definition because of the colon at the end of the symbolic name. And then we have another dot equals to dot plus 256, which is also just telling the assembler to advance by 256 bytes. In other words, we say, okay, mark this spot as original, move forward 256 bytes, mark the next location, okay, 256 bytes after original as reversed, and then go advance another 256 bytes. We don't really have anything else to store, but since I want to make sure that the assembler allocates enough memory for this particular program, I need the line that is currently highlighted, just so that we have that much space reserved for reversed. Okay. And then you have the usual, starting point, with a dot text, because we have been using dot data because we have to specify what goes into the place where you can change. So we need to switch back to dot text so that we can specify the actual code of the program. We have dot global underscore start to export the label underscore start, and then underscore start needs a colon next to it. So when you enter this program, you have to remember to put in the colon to define the start label. And then we have move long original into EAX, move long reversed into EBX. And then you have to put your code in here to implement string reverse, okay, not string. String reverse, do not refer to the labels haystack or needle because there's none. This is borrowed from last year's homework assignment, so some of it is not changed. Make use of EAX, which is a pointer to the original null terminated string, and EBX pointer to the reversed version of original, and it should also be null terminated. But the null terminator has to be put there explicitly, so you have to put in the null terminator. Check here is just a label so that my test script can put a breakpoint here to see if the reversed version of the string is at the reversed label. Does everybody understand what the program is supposed to do? I'll give you a few examples, okay? So let's go ahead and, I'll go ahead and just write the entire program, okay? So we'll display both this part and a part of the editor here. Go to the temp folder. You have to put everything into string reverse as a subfolder, so you have to make a subfolder first. Go to the subfolder, and the source file is supposed to be called strrev.lowercase s. And then you can now start typing. The comments you don't have to type if you don't want to. Okay, so we have original dot equals dot plus 256. Then we have reversed dot equals to dot plus 256. And then we have dot text dot global underscore start and with a colon. Move long original to EAX, move long reversed to EBX, and then you put your code here, and keep the label check here. Make sure you have a check here label, with it's case sensitive, so make sure it's entered in exactly the same case. I'll just put a no up here because we're not going to get that far. So that's kind of a template of your program. In your program, you probably don't want to put a no up here, but put the actual exit code that we need in order to get the program out of here. Are there any questions about the code at this point? Okay, it's just a template. So the next question is, then what do we do about this program? Well, we do the usual thing that we do, okay, right? We assemble the program into string reverse.o from string reverse.s. And then we link the program, strrev.o, there we go. And now we can enter the debugger. But before we get into the debugger, the first thing I want to do is to specify a few files, okay? So I will have to specify a few files just so that I can fill up the original with a null terminated string. And then I will also have to fill, and then your job, the program's job, is to fill up reversed with a reversed version of the original string. Is that okay? All right, so let's go ahead and do something like that. I also include the instruction here in the homework assignment of a tool that you can use in order to make a null terminator in a file, because normally you cannot enter the null terminator in a file, okay, which is basically ASCII code 0, okay? In VI, you can do it by Control-V and then Control-@. That will enter the null terminator. In Nano, I am not aware of any way to enter control characters. But there's an external tool that you can use to also do the same thing, okay? All right, so let me go ahead and do this part here. And what I need is just a whole bunch of gibberish first to put some gibberish into that file that is a little more than 256 bytes. So we'll go ahead and do Control C from here, go back to here, and cat to a test file .txt, and then I'll just go ahead and paste what I have selected from the HTML editor, which is a whole bunch of stuff. Okay, and then press Control D after the paste to end the cat command. And now we have a test file.txt. Okay, there we go. We have this entire file. The file itself has 888 characters, which is more than what I need. So I'm going to trim it until it is the right size. Okay, so we'll go ahead and trim a few lines. If I trim this line, it might be 555. So we still have, let's see, 555 minus 512 is 33. Okay. So I want to back up 33 characters and delete those 33 characters. In VI, there's a quick way to do that. When you're at the end of a line, so let me remove this line first. When you're at the end of one line, okay, now it has 256 characters. I need to remove 32 characters now. Okay, so to remove 33 characters, you can type X, like 32 times, or you can do something like this. Enter the count first, 32. You won't see it echoed on the screen, so I just type 32 on the keyboard, and then I press lowercase x. Oh, that didn't do it. Darn. Okay, I thought it's going to do it because you can
do 32 bits or 32 bits.
32 x's. I want to delete 32.
I know, but then it only took away one character.
Yeah, that's.
So
well, I can do it.
That's the issue.
Yeah, 32h will go back 32 characters. Then I can do a uppercase D to delete those characters.
Oh, so you said H, not X.
Yeah.
Okay.
So H works with the counts, but X for whatever reason does not. So it's kind of bothersome. Okay, so rewrite the file. Oh, 32 is not. Oh, maybe I didn't enter 32. I still have 8 characters, 9 characters to delete. So 9h to go back 9 characters, delete those. And we have one extra, which is, okay, we can just put a space here. Now it's too many. Now it's not enough. Well, it's okay, it's good enough, okay? It's close to filling up the entire space. It's short one single character. Okay, so I save the file, okay, and then do an ls-l just to double check the size of the file. It is in fact 511 bytes, 1 byte short of what I really wanted, okay, but close enough. Okay, now the question is, how do you specify a null terminator in this thing, okay? So to do that, you have to install a program. If it's not already installed, it's called HexEdit. And it is not installed here just yet, so it's perfect. I can show you exactly how to do it. So what you want to do is to change to the root user, okay? And after you change to the root user, the command is actually documented here as well. You have to type, oh, I thought I did.
Yeah, it's right there.
Yep, right there. So this is the entire line of command that you have to do because you have not been updating the distribution for a while. It is probably a good idea to update first and then do a safe upgrade and then install the program. So I'm just gonna copy this command and paste it into here. Press the enter key. It might take you a little bit of time because it depends on how many packages needs to be downloaded to update your distribution. So but the bottom line is we just need to install that little HexEdit program to change 1 byte to a null character. You can do that in VI without having to install HexEdit, but I want to show those of you who do not use VI how to do it. Okay, so it will ask you, yes, go ahead and install that.
This is as the root user, correct?
Yes, you have to run aptitude as root, correct. All right, so while the system is doing this, which is going to take a little bit of time, I'm going to use another shell to show those of you who use VI how to do this, okay? So if you do use VI, you go to the file, okay, and you just say, okay, maybe I'll just test up to this point, okay. So 2 space start is the string, okay, because I want to specify a null terminator here, okay. So to do that, what you do is you can either insert, because we are still 1 byte short, so we can do an insert here, or you can replace this single character here with something else. So to replace is lowercase r, and then to specify the null terminator, it is Control V followed by Control at, which is Control 2. And it looks kind of dim. It's basically a caret followed by an at sign. So if you look, you cannot see it because of the contrast or the lack of contrast, but this is basically what it's showing. It is Control at, and that's the null terminator. Okay. And how do we know that really is the null terminator? Okay, so we'll save the file, and then the hex dump is already installed for sure. Okay, I know this program is already installed in your distribution. So you say a hex dump -c, and then the file that you're testing, that you're writing. And I would suggest you to use a pipe, because otherwise it scrolls off pretty quickly, and press the enter key. So we can see that we have, to start, which is 1, 2, 3, 4, 5, 6, 7, 8 characters, and then the null terminator is supposed to be here. That is corresponding to 0, 0 as an ASCII code. So I know for sure the null terminator is in fact here. Are there any questions about this process? Or have I thoroughly confused the entire class? Yes?
What was the command for putting the null terminator in there again?
Control V and then the Control at.
Okay.
Yep. But that only works in VI. I'm not sure whether Nano can do it or not. But since well, I suppose we can go ahead and Nano it and find out what Nano. Well, Nano does code it as Control at, so maybe Nano can deal with Control at as well. So I'll try it here inside Nano, which is Control V, which is an escape. No, cannot do it. Control V has a different meaning in Nano, so it doesn't seem to be able to escape it. Yep.
If you just, would you be able to enter it by just Shift 6 and Shift 2?
Shift 6. No, it's not the same thing. It's not literally a caret and an at sign.
Okay.
It is one single character, but because it's not a printable character, it is displayed as caret and an at. In other words, in Nano, if I use my cursor to go over to that position right at the beginning, if I press the right arrow again, it will skip the at because it is it's really just one character. But it is displayed as as caret at because that's how it encodes non-printable characters.
So basically, if there is such a command, we can just search for a null terminator with Nano, and it'll tell us the command.
Basically how to specify non-printable characters.
Right.
It might have the ability to do that, but since I don't use Nano, I'm not familiar with it enough to do that. But there's not, you don't need to do it this way because once we install, well, it's installed, it's updating a whole bunch of stuff, so we have to wait a little bit. But once it's done, we can use HexEdit to do the same thing. It's a very easy program to use, and for those of you who like to hack stuff, it's a really good tool for hacking because you can change just a few bytes. I know those of you who want to have infinite life in games and stuff like that, you start with like 20,000 gold instead of 2, okay? And if you know exactly which byte or which bytes control those initialization numbers, you can use HexEdit. Go to those byte locations, change it, so you can now start with 20,000 gold instead of 2.
Is that something you do for your kids in Dota or
in Dota, because they use Flash, there are other ways to do it. There are specific programs that can hack into the memory locations of a program that's already running.
Doesn't that get you caught by like some kind of anti-cheat system they have in place?
I do not know. Since I did not do that, I have never been caught.
Okay.
All right, looks like the other one is done already. Okay, so if it's done, we can use the other command, which is called HexEdit. Okay, it's just like hexdump, except instead of dumping, we are editing. And you can go to testfile.txt, press the enter key. Now it is quote unquote an editor. It looks almost exactly like hexdump because on the left-hand side, it still has the ASCII code in hexadecimal, and then on the right-hand side, it still displays everything in text as much as it possibly can. So once again, you use the arrow key to go to the location where you want to change it. So once you get to the location where you want to change it, just type it. Okay. So just if you want this to be a line feed character, then this 0A. Okay. So now it is altered. You can see it's also in boldface, just to highlight the portion that is changed. But if you want it to be a null terminator, it has to be 0, 0. It is just as simple as that. Okay. Okay. Now that you're done with all the typing, it's time to save it. And of course, I don't know how to save it. Control X works. Okay, so it has the same key binding as Nano. So Control X will exit and will ask you whether to save the changes or not. You can say yes, and then it will be saved. So are there any questions about how to put that weird, null terminator in a text file? Okay, no questions? Okay, so with this part done, okay, we're going to test the program, right? So to test the program, we have to use GDB. It's called string reverse, like that. List the program. We'll put a breakpoint on line 9. It doesn't really matter where we stop. Run the program. Now it has stopped. So the first thing we want to do is to say, okay, show me those 512 bytes starting at original. So x/512. Okay, you may not want to use 512 because it's going to scroll a lot. And then b, and then bx. Okay, so ampersand original. And they're already zeros, okay? But don't count on these bytes being zeros to begin with, okay? That's the whole point. Because when I test your program, I will pre-initialize these locations not to be zeros. So you cannot count on it. Okay? So the next question is, how do we, load the file that we have edited into this area?
Restore.
Yep. Restore. File name, which is testfile.txt, binary,
the
ampersand, and then the label name, which is in this case original. Okay, now by loading it at the label original, I'm also going to overwrite the other 256 bytes, or 255 in this case, that is starting at the label reversed. Because original is the start label, and then we have 256 bytes allocated, okay? But this file has 511 bytes, which means it is going to not only overwrite the 256 bytes starting at original, it will also overwrite 255 bytes starting at the label reversed. So by loading one single file, I'm initializing the entire space that I have allocated short of 1 byte, okay? Okay, so let's do this, and then we'll figure out what it is actually doing. So we'll do the same thing as before. We'll display original, and this time we'll use the BC, which means we're going to display characters as much as possible. And you can see this time it does display a whole bunch of characters, and here is our null terminator. Okay, is that okay so far? Okay, now we want to say, okay, but what about reversed? So reversed only has 256 bytes allocated at that point. So we press the enter key, and you can see that space is also initialized. Okay, which is fine. Okay, because I want your program to only change the first 9 bytes of this area. So it is going to spell the first 8 characters of original backwards, followed by a null terminator.
So when we reverse it, the null terminator will be first.
Okay, so if original, okay, this is an example. So if original as a label has the following bytes, okay, we'll just say A, S, C, F, and then the null terminator, okay? I want reversed as a label. We want F, B, S, A, and a null terminator. Now the key point is you have to include this null terminator in the test file itself, because you cannot count on memory having that null terminator to begin with. And this null terminator, your program has to put it there, because this part of memory space is not initialized. So you cannot count on having this null terminator pre-filled at that space. Is that okay so far? Okay, so how do you make this work? Well, I wouldn't get into assembly coding right away. I would write a C program that can do something like this, and then I will, translate the C program into assembly. And I'll even give you the C program to do this. The C program is relatively easy, okay? So if I were to do this, you want to use string there, I can just do everything with regular C and use GDB to debug it, okay? So I'm going to write a original string like this, okay? Char string open original open close bracket equals to, and then we specify a string here. So we can just say, give me something that is interesting if you spell it backwards. Yeah, I know exactly what. Race car. Oh, murder. You guys know that one, right? How many people live close to Davis? Okay, red rum. Yeah, exactly.
Burger.
Murder burger.
Yeah.
It becomes red rum because the Davis residents or the city council decided, that's not a good name to have. So the burger place, just said, okay, we'll change the name. We'll reverse the spelling. It became red rum. So we'll say red rum. And then they'll reverse it, right? Okay, so here's those, and then we have the reversed string. So the reverse string, you cannot do it the same way because it is not initialized. So we'll just reserve a whole bunch of space here. We'll say, okay, we'll reserve 256 bytes and uninitialized, okay? All right, so here's the code, okay? What do we need to do to get this to work in C and C++? All I want to do is to spell the string in original, which is supposed to be null terminated. I want to spell it in a reversed way and put it into the string called reversed. So what is the first thing you have to do? Well, you have to know how long it is. Because until you know how long the original string is, you don't know where the end is. Okay, so you have to find the end first. To find the end is fairly easy because you just need to scan the original string until you find the null terminator, right? Okay, so we'll go ahead and do that. There are several ways to do this, okay? It depends on how you want to do it. We can use a pointer, right? We can use a pointer, actually to do this correctly, okay? This is the way it's supposed to be, okay? Because if we're not going to change red rum itself, we're going to change reversed. So to do it correctly in C and C++, I should have declared these as const. So I would say this is a original pointer, okay, or PTR to the original string. Okay, there we go. All right, so we need a for loop. The first thing we need to do is to initialize that pointer to point to the very beginning of original. And then the next thing we need to do is to specify the condition to stay in the loop. In other words, under what condition am I going to stay in the loop? In C and C++, it gives you this option, which is really kind of cryptic, but it will get the job done. All I have to do is to say asterisk, which is dereference, PTR original, and that's enough. Okay, that's a conditional expression already. Because by dereferencing the pointer, what do I get? I get a character, right? But a character is basically just a number, which can be a 0 or a non-zero. If it is a 0, it is the null terminator. I'm done. I found the end of the string. Okay? But if it is non-zero, if it's non-null, that means I have not found the end of the string yet, and I have to keep going. All right? So we'll worry about what to do in the loop next. But what about the post operation? After each iteration, what am I supposed to do? Just increment the pointer. Okay. Now, since this is not on the right-hand side or any expression that needs to use the value of the auto increment, you can use a pre-increment, you can use a post-increment. It makes no difference whatsoever. This is the part in parentheses of a for loop. What do we do for each iteration other than incrementing the pointer? Well, it's up to you. Okay, you can do certain things about this to make your job easier for the next phase, or you can kind of not do anything because you just want to find the end. Okay, so there are different ways to look at this. You know, it's up to you guys to decide how you want to do this. Okay. Let's see, which way would be easier? There are so many different ways to do this. I will leave it up to you guys to decide how you want to do it. But one way to do it is simply to find the null terminator. Okay, so by the time we get out of this loop, we would have found the null terminator of the original string, which is great because now we know where the string ends. So now we can start to put those bytes into reversed, but in the reverse order. Okay. All right, so that means we need another pointer, right? We need another not const this time, it's just a regular char. And this one is ptr to reversed, okay? It is a pointer, like that. And then we'll say, we'll initialize ptr reversed to be reversed. So at the beginning, starting at the beginning of the destination string, okay? And then what are we going to say? Okay, I'll leave these things alone for now. Okay, we'll specify those later. Okay, what do we need to do for each iteration? Well, we need to copy something, right? We need to copy something from the original string into the reversed string. But since the ptr original is now pointing at the very end of that string, what we need to do is to go backwards, okay? So we basically want to say ptr, or dereference ptr reversed, is going to be this needs to be fixed later, okay? But I'm going to give you the general idea of what we're doing here. So we are basically saying, okay, we are copying byte by byte from the original string into the reverse string. Okay, the pointer to the original string is pointing to the very end, which is actually the null terminator, and the pointer to the reverse string is starting from the beginning. Okay, so in general, we know kind of what we need to do as a post operation. We need to, one needs to be decremented, which is the ptr original, and the other one needs to be incremented, which is ptr reversed. Okay, because one needs to go forward, the other one needs to go backwards. Okay, but there are minor details that we have to deal with. When are we going to stay in the loop? When do we get out of the loop? That's one of the questions. Okay, so does anyone want to think about this? You know, when are we going to stay in the loop? You can compare pointers to addresses, right? So what are we going to compare to what to stay in the loop?
The original pointer to the first.
Yep.
Original.
Okay, very good. So we need to compare original. Okay, okay, so we need to compare ptr original, which is a pointer, to the start of the entire array, which is just original. So we need to use some kind of comparison between these two so that we can decide whether to stay in the loop or get out of the loop. So now the question is, when are we going to get out of the loop and when are we going to stay in the loop? Well, what do you think? You have to remember that we have to copy the very last byte too. And then there are several things you can do about this. You know, one is, I don't want to combine dereferencing with auto increment and auto decrement because that can be kind of confusing. So we want to do things kind of in a much more straightforward way here. Okay, so what do you think? Well, because we have to do this part here, so that means as long as ptr original is greater than or equal to original, we want to stay in the loop. Is that okay? Any questions about this part? But that also means there's one problem because PTR original is pointing to a null terminator to begin with. So that means you have to kind of back off a little bit first, back off by 1 byte before you do this. Okay, so we'll go ahead and back off by 1 byte between the loops here. So we say minus minus PTR original because we don't want it to be pointing at the null terminator when we start the second loop. Are there any questions about this part? It really is, these are really just the detail thing, but you need to take care of the details for this code to work. All right. What do we do after this? After the second loop, don't we have one little thing to do? Add the null terminator to the destination, which is not going to be very difficult because PTR reversed is already pointing at the location. So we just have to say PTR reversed equals to 0. This is the null terminator. And that's it. That's the entire program in C and C or C++. Okay, this is fairly generic code. You can use C or C++. All right. Are there any questions about this code here? Is there any doubt that this is going to work? I always have doubt of my own programs, okay? As a general rule, I do not know. Okay? So what I'm going to do is, guess what? Test it, right? Yeah. Okay, G++-G-O, I'm just going to combine the compiling with the linking, okay, because it's a single source file program. And then we'll gdb string reverse, list the program, and because I'm fairly confident this is working, so I'm going to put a breakpoint on line 16, and just for cuz I will put a breakpoint on line 8, just so that we can examine the arrays before, and then we'll examine the arrays after. Okay, so run the program. Now we're at the very beginning of all that code. We say, okay, tell me what is in original. Okay, that should not be surprising. It's just red rum. Okay, tell me what is in reversed. Now remember, this time reversed is really uninitialized, so we get garbage. Okay, that's expected because reversed is not initialized. Is that okay so far? Sort of. Okay, so since I'm fairly confident this program is going to work, I'm just going to continue, and it does get to the end. And then I'll do the same thing. The first thing is probably not necessary because I marked original as a const char array, and I also marked the pointer going through original as a const char pointer, and the compiler did not complain about anything. I'm fairly sure that I did not overwrite anything in original, but it's always good to double check. Okay, so original is still good as the original string. And now we want to say, okay, but what about reversed? What is in reversed? Oh, it's still a whole bunch of gibberish. Yes, the rest of it is still a whole bunch of gibberish, but you can see murder with a null terminator is in it already. Is that okay? All right. Now the rest is already, it was here to begin with. You can see a whole bunch of null characters here, followed by a ASCII code of 1. That is still here. Okay, I have not overwritten that portion of memory. I just overwrote the first 6 characters with MURDER and the null terminator. The rest, starting from here and all the way till the end of the entire array, was untouched. Are there any questions about the C program itself? Because remember, we already talked about how to convert from high-level code into low-level code. Okay, that's what we talked about on Tuesday. So now you have to apply those techniques to convert this program, which is known to work in C++, into assembly code. Now, if you feel that, oh, Tag, I don't like the way that you wrote your C++ code, write your own. Okay, you do not have to use my version. And I can kind of tell that some people may be wondering and say, but Tag, you never really taught us how to convert a for loop into a non-structured code and then into assembly code. We only talked about a while loop and a do while loop, but what about a for loop? What do you think as a class?
We would like an example.
Okay, I will only give you this piece. If you have a for loop, okay, a for loop has 4 pieces. Okay, it's got A, which is the initialization, a semicolon, a B, which is the condition to stay in the loop, another semicolon, and a C, which is specifying the post operation after one iteration. And obviously it has a D, which is the statement of the loop itself. So a for loop has quote unquote A, B, C, D, there are 4 parts to it. To translate this into a while loop, you say A, that's the initialization, gotta do it before the loop, right? And just for syntax perspective, you have to put a semicolon here because A is supposed to be just an expression. Okay, and in C++, if you want to turn an expression into a statement, you need to put a semicolon. So technically speaking, A needs a semicolon after that. And then you have while. B is the condition to stay in the loop. It stays here, which is the condition of the loop. And then inside the loop here, I need to use curly braces. Even though this is just one statement D, I need the curly braces because D goes first here. And then the post operation, which is C, goes after that. But remember, C itself is just an expression. So for syntactical reason, you need a semicolon after the expression to turn it into an expression statement. And then close curly brace, that's it. So this is a for loop. This is the spelled out version of a for loop as a while loop. That's it. Once we turn it into a while loop, then all the notes that we have talked about would apply. See, Lego pieces, right? Once we make one connection to one piece, the rest are now connected. But that is something that you should have gotten from your CISP 360 class. The equivalence of a while loop and a for loop. Are there any questions about this code? No questions? It's all good? Yep, go ahead.
Well, not really about the code, but about this assignment. So what we'll do is we'll have a text file that'll just be completely filled with gibberish, and then we just turn one character into the Null Terminator.
Yes.
And then what our code will do is read up to the Null Terminator and just reverse that section. Into,
Correct. Yes.
Into the other.
Yes, but you have to do about the same thing as this program, which means the reverse string has to start from the beginning of the reverse string. So you're not reversing everything. You're basically okay. Let me just go back to the assembly code so I can finish that part. But I will be emulating what your program is supposed to do. Okay. So that would be GDB. Oh, I have to relink that because otherwise, strrev is now the C version. I have to regenerate from the assembly version. There we go. Okay. Put a breakpoint on the first instruction, run the program, and we want to use restore. How do you run restore again? File name, binary into the address of original. Okay, there we go. And then we can do well, I'm not going to display the whole thing because I know the string is fairly short. So I'll just display the first 16 bytes of starting at label original. Okay, so in this case we have TO space START as the string, right? So your program, as the quote-unquote output of your program, you have to spell TRATS space OT at reverse, okay? But it has to be at the beginning of reverse. Let me just do that manually first, so that way you know what you're supposed to do, okay? So to do this manually in GDB is a little bit cumbersome because it really does not have a way to deal with characters. So the only way that I can do this more kind of in a way that I know for sure will work is to use set var, and this is going to be really cumbersome because I have to cast the address of reversed into a char pointer first, and once we cast it into a char pointer, we can do arithmetics. So the first one is going to be the T, the second one is the R, the third one is the A, and then we have the T again as the fourth character, and then we have S as the fifth, a space for the sixth, and a lowercase o for the seventh, and uppercase T for the eighth. Because that will spell it out backwards, but don't forget the null terminator, right? So you have to remember to put a 0 into the 9th character because that is the null terminator. Because otherwise that character is not null to begin with. You have to put in the null terminator. So now that we have this, we can display, okay, do a memory dump starting at reversed, there we go. And it does spell out TRATS space O uppercase T and a null terminator. That is the expected result of your program. Is that okay? Now, obviously, in your case, you're not going to do it in GDB. Your assembly code will accomplish what we just did. But that's how I'm going to test your program. I will give you the test case, which is specified in the input of a file. And when we get to the label check here, my test script will compare the memory content at reversed with what it is supposed to be, up to and including the null terminator itself. Is that okay? Yep, go ahead.
Is there a way to just directly convert for loop into the assembly without using while?
Do you want a long answer or the short answer?
Short.
No. Which, by the way, is also the long answer. Because in assembly language programming, the only thing you have is a conditional branch and a way to compare. So you have to basically do a compare first and then use the result of the compare to decide whether you want to branch or not.
I have a trouble to translate the asterisk symbol in C into assembly language. So
Okay.
can you show us that real quick?
Well, I'm not going to show it to you, but I will talk about the concept related to that. Okay? All right, so let's get out of this program because this is really just an illustration of what your program is supposed to do, but not showing you how it is going to do it. So I'm showing you the what, but not the how. Let's go back to the C code here. So your question is, what are we going to do about this? And what are we going to do about that, right?
Yeah.
That's your question. Okay, what is dereferencing in C and C++? So let's go back to cisp310 and just remember what is dereferencing. What does it do? Well, can I dereference an integer? So if I have int x, can I dereference x? Okay, let me just write it on the whiteboard so we can see it. So I have a variable which is just an integer, regular integer, nothing else. Can I do something like that? Would that be possible? That would not, it wouldn't even make any sense, right? Because it's an integer, and what do we do with integer? We do calculations with integer, but we don't dereference integers, right? Okay, so what can you dereference? It's only when it's a pointer, right? When it's a pointer, it stores an address, and when it stores an address, you can dereference. But why would you want to dereference? So this time, let's say we have another variable y here. Okay, so this is all going to be okay. So I have a regular integer y. I store the address of y in pointer x, which means x now has the address of y. Okay, but x itself is an address. Okay, it's a pointer which stores an address. So what does it do? The statement itself. What does asterisk x means? Are we storing 2 as an address, or are we storing 2 to where x points to? We are storing 2 as a number to where x points to, which according to this is just where y is, right? So we're actually initializing y with a value of 2. Do we have a mechanism like that in assembly language programming? Do we have an addressing mode of these operands that can accomplish the same thing?
Indirect.
Indirect, exactly. Now, indirect is not quite as general as this. It can only use registers inside the parentheses, but you can load whatever you want into a register. You can move along something into a register, right? Okay. So if we can do this, what about this part here? Can we do something like this in assembly? Can we increment?
Yeah.
But we haven't really talked about the increment instruction. Do we need an increment instruction to do this? Because increment, after all, is just a shorthand of adding 1, right? Okay. What about this part here? Can we compare? We're comparing a pointer to a location in memory. Can we do that? Well, first of all, we have a compare instruction, right? So the question now is, can we compare a register that so happens to be a pointer with an address? Yeah, we can do that. So that pretty much, covers everything. We have all the pieces. The question is, how do you put the pieces together? Okay? Is that all right?
Yeah.
Okay. So when you write this program, you don't want to convert this entire program into assembly in one single shot, okay? The first thing I would do is just the first line of this code. In other words, the first thing I'm going to do is just to implement one loop to find the null terminator of original. That's all I want to do, okay, to start off with. Because if anyone has any misconception about what a register is, what is the difference between a register operand as opposed to an indirect operand, the differences between an immediate operand versus a direct operand, how to compare stuff, and stuff like that, implementing this one statement will help clarify a lot of those misconceptions. And once those things are clarified, the rest of the program is just more chore, but it's not a whole lot more concepts involved. Okay, so I would do this program, really, really step by step. First thing, just find the null terminator. Don't even try to change anything. Just find the null terminator of original. Okay, because if this is successful, then when this loop exits and you look at the pointer, it points to a null character. It should point to a null character. Which means in your program, the equivalent register should also point to a null character. Any other questions? No other questions? Just silence. How many people have been exposed to really basic instructions in a programming language like what we are dealing with here in assembly language programming? Guess no one has any exposure to like low-level calculator programming stuff? No? Can you program the TI calculators? They're not programmable?
Yes. Can I, or is it possible?
Okay, so if it is programmable, what is the programming language for those calculators?
For the TI-89, you can use assembly.
You can use assembly? Is it like native assembly to the processor, or it just looks assembly?
I'm not too sure.
Okay, I will show you this as a context. It's not really, it's sort of related to this class, it's sort of not. Okay, when I grew up as a kid, I grew up with these calculators. It's called a Casio FX601 or 602P, depending on whether you want the high-end version of that or not. Okay, Yeah, this is that's a calculator that I did not grow up with, but I wish I did. Okay, all my friends have that, and then my parents said, "Tech, you don't need a calculator this complicated." So they gave me one that has 31 steps of program steps. This thing has like 512 steps, I think. Okay, so, and I wrote games on these things. I borrowed these calculators. I borrowed one calculator from one friend, and I said, and I asked, can I borrow your calculator over a weekend so I can write a game on it, and you get to keep it, the game itself, right? And he said, okay, sure. I'm not doing any homework assignments and so on. And this is the programming steps. Okay. So you have really basic stuff to retrieve. It has memory locations, kind of like registers. It even uses the name of registers, right? So min is not min. It's memory in, which means store into register 00. It has 100 registers, okay? And you have label, okay? Label 0 to mark the label. And you have DSZ go to 0, okay? What is DSZ? DSZ is decrement memory register 00 and go back to label 0, which is what this 0 is, until register 0 is 0. So it does have kind of a concept of a compare and also a branch in like two instructions. But this is the stuff that I grew up with, which later on I found out, hey, assembly language programming is about the same. So that's why this stuff kind of is not as difficult for me, because I grew up with these things when I was in 8th grade, so 8th, 9th grade or so.
Did you ever have a Commodore?
No, I never had a Commodore, but I did have a Pineapple.
I have no idea what that is.
It's an Apple II Plus, clone.
Oh.
Yeah, so they have Pineapple. They name all those things as different types of fruits. They have oranges, they have pineapples, they have peaches and stuff. But they're all basically Apple II Plus, clones. So anyway, this is factorial, but not using a recursion. All right. Are there any other questions about this new homework assignment? Now, it's due next Thursday, which means I cannot give you the exam on the same day, because I do want to go over the solution of this before I give you the final, I give you the second exam. So the second exam is going to push to the Tuesday after that. So that would make it when? Let's see. It's still before Thanksgiving.
24th.
The 24th? Okay, let me just take a look at the calendar. Well, the reason why I want to do this is because doing the homework assignment is really the best way to study for this class, and I do want you guys to use this as an opportunity to study. It's not going to help people who don't want to study to begin with, okay? But for people who want to study but don't know really how to get started, and how to study, this will help. Cannot find it. There we go. So I'm going to put a new event here, just so that I can remind myself. Exam 2. Okay. Exam 2 is going to be. Okay, today is the 12th. This is when the homework assignment is due. So the 24th is going to be when the exam is going to be scheduled, which is like the Tuesday before Thanksgiving. At 9 o'clock in the morning. And the duration is, well, the length of the class, which is 80 minutes. So now it's in the calendar, in the Moodle calendar. I mean, so it shows up, on the calendar, so you can remember that we have an exam in a week and a half or so. All right. Any other questions?
So So we'll go over the practice exam on Tuesday.
Yeah, I think that's probably best is to go over the practice exam on
Or
Tuesday.
else we forget.
Yeah, exactly.
Just
Well,
do it today.
because when I go over the practice exam, it might help you with your homework assignment as well because it really is the same stuff, the same material. So after you work on this homework assignment, hopefully over the weekend a little bit, the practice exam is going to test you on exactly those concepts. So hopefully if you work on the homework assignment over the weekend, on Tuesday when we talk about the practice exam, you guys will feel, hey, it's the same stuff. I kind of know this stuff already, and you feel comfortable with all that material. Okay. So let's see, what is the time? And we still have 15 minutes, which is great because now we can move on to the stack. And where am I? Wrong place. That's where. So I want to go to. Okay, so we are pretty much done with assembly language programming. This entire section, this entire topic, we're kind of done with this already. And the next topic starts on subroutines. And subroutines we cannot start right away with subroutines. We have to start to talk about the stack first. So this is the ordering of the topics. So if anyone is interested what do I read to read ahead of the class? Just follow this order. Okay, this is the order of going over all of these topics. Okay, so the first one is the stack, which doesn't seem very exciting. Okay, what is the stack? The stack is basically a LIFO structure. It is for storing and retrieving, stuff. Okay, it's last in, first out. In real life, we have a lot of things that are last in, first out, and many of those things really should not be last in, first out, but they end up to be last in, first out. Okay, prime example: your refrigerator or the freezer. Okay. Does anyone have one of those, like dedicated freezer where it opens, the top opens and you put stuff into it? Okay, that's a typical example of something that is LIFO but should not be LIFO. Okay. So let's say your parents, drove to Costco, okay, and they bought, $600 of food, and they put it into the freezer. Okay, and by the way, they bought the freezer from Costco as well. So they first plug in the freezer, and then they put $600 worth of food into the freezer. Okay. What do you think is going to be your first meal? Or what kind of food are you going to have as your first meal? So let the top layer, right, which is the last thing that you put there, right? What about the bottom stuff? Okay. What about that rack of lamb that you bought, and it was the first thing, because you're so excited about the rack of lamb, you go like, oh, I like this, maybe put it into the freezer first, right? When are you going to have a rack of lamb? Never. Until you move, right? Because when you move, you have to unplug the thing and you have to clear out everything from the freezer. Then you're going to get to the bottom. That is last in, first out. Okay, the last item you put into the freezer is the first thing that you retrieve from the freezer. Okay? So even though it is kind of annoying in real life in many cases, it is really useful in programming. And we have been using last in, first out since elementary school. Okay? Believe it or not, this is what we have been using since elementary school. When did you first encounter the concept of parentheses in regular, just normal mathematical expressions? Elementary school, right? I mean, you use parentheses to group things. Okay, so we'll just go ahead and use an example, and I'll show you why we have last in, first out in that concept. Okay, mousepad, and we'll do something that's not exactly complicated. Okay, so we'll just say I want to calculate the expression of 2 plus 3 times, and then we have 4 divided by 2 minus. And then we have another thing here. So we'll have 5 divided by 2 plus 3. And now I have to match the parentheses. Okay. 1, 2, 3, 4, 5, 6. Okay, there we go. Okay, so this is a kind of long and drawn out example. Okay. But what do you do when you deal with expressions like this? go all the way inside, right? And how do you know where to get back to once you're done with the 2 plus 3? How do you know what is the next step? The next one out, right? This is last in, first out. Okay, this is LIFO. What about in C? Okay, I'm just going to use this, kind of really primitive example in C. Okay, so in main you call F, okay, and in F you call G, and in G you call H, and so on. Okay, so by the time you get to H, which doesn't do a single thing, what do you do next? When you're done with H, H is returning. Where does H go back to? It goes back to G, and then G goes back to, when G is done, it goes back to F, F goes back to main, and then main exits, right? That is also last in, first out. Is everybody convinced that this is actually last in, first out? Okay, all right. So last in, first out is really useful as a concept, okay, in programming in general. For those of you who want to write compilers and stuff like that, the concept of a push down automata, okay, is based on a stack basically. Okay, it's like a Turing machine except it doesn't have a tape. Instead, it has a stack. Okay, and that's one of the most useful practical quote-unquote automata or machine in computer science. Okay, so now that we know what is a stack, let's talk about operations that you can do with a stack. You can put things in a stack. You can retrieve stuff from a stack, just like a freezer. Okay, every time you look at the word stack, think freezer. Okay, I can put things into a freezer. I can fill it up a freezer, right? I can get things out of a freezer, and the freezer can be empty. If there's no item in the freezer, it is empty. Okay, a stack is exactly the same way. Yes.
But can you add to the stack? Can you pass?
Can you make the capacity of the stack bigger?
Yes.
You cannot. The operating system is pre-allocating a chunk of memory for your stack. So even though the stack is initially pretty much empty, the capacity of the stack is fixed. Just like a freezer. Okay, you buy a freezer. Okay, you may have a really big freezer and it's empty. But you cannot increase the capacity of the freezer on the fly, and the stack is really the same way. Okay. All right. So there are several operations you can do with a stack. Okay. First of all, there is something that we call the stack pointer. The stack pointer, which also has the name of ESP for Enhanced Mode Stack Pointer, because the original stack pointer SP itself is a 16-bit register. But 16-bit is not enough to deal with a 32-bit architecture, and that's why they call it ESP for Enhanced Mode Stack Pointer, which is 32-bit wide. This is a whole bunch of stuff, but the bottom line is the stack, quote-unquote, grows down to lower addresses. In other words, when the stack pointer is high, that means your stack is relatively empty, and as you put more things onto the stack, it goes lower and lower. Okay. So I'm not going to spend too much time here because just talking about the stack pointer is not going to be helpful. So what I would do instead is to go back first. It doesn't give me. Oh, there we go. Go back up, and what we'll do is we talk about these instructions. Okay. There's an operation called push, which is putting things into the freezer, and there's another operation called pop, which is removing an item from the freezer. Okay. So push puts something into the the stack, and pop would remove something from the stack. Okay, so let's just take a look at some examples here. These are the specific instructions. Okay, not very exciting. You can read about this. I'm not going to spend too much time to read all this stuff here because we will take a look at an example like this. Okay, so let's go ahead and write a program to illustrate it. I'll just call it stack.s. Okay. Now with a stack, you don't need to have a data section anymore. So you can just start with .global _start _start. And what we'll do is we'll say, are we running out of time? No, we still have 5 minutes. So we'll push something on the stack. Okay. Now, in the i386 instruction set, you can push just about any operand. You can use immediate, you can use direct, you can use indirect, you can use any operand you can specify in other instructions. Okay, so I'll just go ahead and be lazy and specify a like 5. Okay, this is immediate 5 as an operand, and I'm gonna push maybe something else like a word, and it stores the let's say the ASCII code of T. Okay, and then we're gonna pop it. Okay. So when you pop, you are removing something from the stack. But when you remove something from the stack, you have to give it a destination. You're going to say, oh, I'm removing the next rack of lamb. I'm removing this rack of lamb from the freezer. But then you have to say, where am I going to put it next? Okay, so you have to give it a destination. And pop W is going to remove a 16-bit thing from the stack, and you have to specify a 16-bit register in order to store that. So I'm going to use AX for this purpose. The next thing, because it's last in, first out, and T is the last thing that we put on the stack, so it is the first thing to get removed. And because we push the 5 first, it is the last thing that we remove. So the next one is going to be pop L, and we'll put it into EBX, okay, as a 32-bit register. And that's the entire program. That's all I'm going to do here. I put a no op here because we're not going to trace it past that end point, so it's not necessary to write the actual exit code. Okay, so we'll go ahead and do a assemble link and GDB. Okay, put a breakpoint on the first instruction. Oh, cannot access memory at location. There we go. Okay, so I did put a breakpoint here, and then we'll start running the program. All right. So what I want you guys to do is to pay attention at the stack pointer. Okay, this is before the push instruction, before we store anything. So I'm going to use IRESP to look at the stack pointer. The stack pointer, unlike EAX or EBX, ECX, and EDX, the debugger does not show the base 10 version of this because there's usually no use of the base 10 version of the stack pointer. Okay? Because we don't use it for calculations. It's not used for numbers. Okay? Then we single step the push instruction, and then we take a look at the stack pointer again. Have you noticed how the stack pointer has changed? Okay, what about the amount, the difference from before the push instruction? How many bytes is it off now in terms of the address?
4.
Off by 4. Very good. And what is a long? Push long. A long is 4 bytes. Okay, so that's what it is. Okay, the stack pointer points to the very last thing that you push on the stack. Okay, how do we know that? How can we confirm that? Well, the X command can be useful for this because X is for examining memory locations. I want to look at one single thing. It is a 32-bit, so W is what you use in GDB because W means 32-bit in GDB. And we want to display as a decimal number, okay? So decimal number is fine, because it's just 5 that we push on the stack. And then we can just say ESP with a $sign because we are using ESP as a register to supply the address where we are examining. And press the Enter key, and it says, oh, it's 5. Okay? So when you say push $5 or push long $5, it is actually pushing the 32-bit representation of 5 on the stack. But by doing that, it is changing the stack pointer. It will lower the stack pointer by 4, which is the number of bytes that we are using to store the value 5. But the stack pointer points to the very last item that we push on the stack. So when we single step, we are going to execute this instruction here. We are pushing the ASCII code of T as a 32-bit number, right? So let's take a look at confirm that. Okay, the first thing we'll do, well, we can confirm both at the same time actually in this case. So this time it is going to be a half word. A 16-bit thing is called a half word as far as GDB is concerned. And we want to see it as a character, not as a hexadecimal number. So 1HC is what we're going to specify here. And once again, we say, okay, show it at where the stack pointer is pointing at. And what do we see? We see the ASCII code of T. Okay? But when you compare what the stack pointer was pointing at before and after, how many bytes are, what is the difference? 2, okay? Because a word is 16-bit or 2 bytes. And what is the stack pointer pointing at right now? The first thing that we push or the second thing that we pushed? The second thing. It always points to the last thing that you have pushed but have not retrieved. Okay? But what about the first thing? Is it still here? What do you think? It's still here. How can we see all of them at the same time? Well, you can say B, we display byte by byte. There are 6 bytes that we have pushed on the stack. And this time we'll use hexadecimal because that's really the best way to display things when they're not organized, as numbers. So we have these things on the stack right now. Does it make any sense? What is 7.4? What do you think is 7.4?
T.
7.4 is the hexadecimal version of the ASCII code of T. What about that 00 after the 7.4? Why is it there? Because it's little endian and it's 2 bytes, so the most significant byte is 0. So 7400 is the very last thing that we push using the push W, the push word instruction. What about the 05 and then the 000000? That's the 5 that we pushed first, right? Okay. So we're running out of time, but I do want to show you the other 2 instructions. Single step. This is popping a word into AX. So I want to say, hey, what is in AX? It is 116. But if I display as a character, it is lowercase t. So I'm retrieving something from the stack and putting it into a register. But that also means the stack pointer is not going to point to the same location anymore. Okay? The stack pointer is now pointing to the first thing that we push on the stack. Because once you pop, okay, the stack pointer is going to move up so that it is no longer pointing to the thing that you have retrieved. It is pointing to the previous item that you have stored on the stack. Okay, so it is kind of automatic. The push and pop instructions would adjust the stack pointer automatically to get this done. So we're going to single step this instruction, which is the last instruction, and the last instruction that we executed is pop into EBX. And what do you think EBX has at this point?
5.
What is the value? 5, exactly. Okay. So this is a very simple run of a program making use of a stack pointer. And in your spare time, you can try to reverse the order of those 2 pop instructions and see what happens. Okay, because you can see that the stack is really just one contiguous piece of memory. There's no such thing as, oh, this is a 2-byte thing, that's a 4-byte thing. It's just 6 bytes that we have on the stack. How you want to retrieve those 6 bytes is up to your instructions. If you specify the instructions incorrectly, it will retrieve things out of order and in a weird way. Okay. Alrighty, well, we're running out of time today. I will be at the lab later on. If you are going to work on your homework assignments and have questions, that's a good time to ask.